Alright, so welcome to another unit of Physics 11. Those of you who are astute and are watching the videos very carefully and noticing details, you will be able to tell some of these I recorded a year later. Some of them were in the 23-24 year, some of them were the 24-25. So you'll be able to tell, maybe, if you're able to look closely enough. This unit is all about kinematics in 2D. Last unit was in 1, now we got 2. So let's dive right into this. We got our purposes for this lesson. First, we're going to understand what reference frames are. Those are very important to solve problems involving relative velocity, and that's what we're going to do. So reference frame, they're actually quite important to be able to understand what's going on. As you can see from this picture, based on your observer, so depending on which one you are, if you're the bearded one or the non-bearded one, you will see something different. So one sees a 9, one sees a 6. This is actually something we're going to consider in physics because depending on your reference frame, you will observe something different. For example, imagine you're sitting on a moving train. In the seat across from you, there's a giant kitten. From your reference frame, it looks like the kitten is at rest, no matter if the train is moving or not. You will see them just sitting there on the seat. Whereas if you have a friend who is standing at the train station and watching the train go past, they will see the kitten through the train window and observe that the kitten is moving with the train. Depending on which person you are, you will see different things. If you're on the train, you'll see the kitten at rest. If you're outside the train, you'll see the kitten moving. This is different reference frames. Depending on your point of view, you will observe something different. Now, in both cases, the kitten's still moving, but it's just based on your perspective. So you kind of need to put yourself in a different position to be able to observe what's going on. So let's look at this same example, but put some numbers in there. So let's suppose the train is moving to the left, 5 meters per second. The person on the train is moving 2 meters per second towards the kitten relative to the train. Meaning, from someone who's on the train, they will see the person moving 2 meters per second. We want to know what is the person's velocity relative to the ground, i.e. what is the person on the ground, what do they actually observe. So looking at this, here's the equation we're going to use. The velocity of the person relative to the ground is going to equal the velocity of the train plus the velocity of the person relative to the train. I know that's a handful, it's a mouthful to even say. So we've got different velocities. We have a velocity of the train, we have the velocity of the person relative to the train, and we are looking for the velocity of the person relative to the ground. So the train's velocity is -5, negative because it's moving to the left. The person on the train is also moving to the left, so -2. Add those together, -7. So the person on the ground will observe that the person on the train is moving 7 meters per second to the left. Let's do the same thing, except now the person on the train is moving to the right, 6 meters per second, while the train is still moving 5 meters per second to the left. So again, notice here, the observer sees the person moving 6 meters per second to the right. I didn't say it's 6 meters per second relative to the train. I said it's relative to the ground. So now I want what is the velocity relative to the train. So we're going to use the exact same equation. We're just given different numbers. We have that the person relative to the ground is 6. That's what the person there sees. And the velocity of the train is still the same. We're looking for the other one. So we get positive 11 meters per second as our answer. That means the person is moving to the right 11 meters per second relative to the train. Now, if the train is 300 meters long, we want to know how long would it take for the person to walk from the front of the train to the back. Now, we are given a distance that is relative to the train moving. We have this situation. The distance of the person to the train relative to the train is equal to the velocity of the person relative to the train times time. So d equals v times t. You've seen that equation. Now we want all of our distances and velocities relative to the train. So we've actually solved for the velocity relative to the train there. There's your time. So it takes 27.3 seconds to go from the front to the back of the train. Again, note here that since we are given the distance the person travels relative to the train, not to the ground, we use the velocity relative to the train. So you just need to make sure you are relative to the exact same thing. Now let's look at the travel distance relative to the ground. So same equation, except we're relative to the ground instead of the train. And we have all that info. We have the new time. Plug that in. So the person on the ground observes that the person on the train is going 163.6 meters to the right. Again, note, since we want the distance relative to the ground, we use the velocity relative to the ground. There you go. So there's some examples of relative velocity involving people moving, and you'll get some other things like that. See you next lesson. Okay, so this clip is from a movie called Wanted. I actually have not seen this. When I saw the trailers for it, I saw how terrible the physics looked in this, so I just didn't even bother with it. Yeah, so I will show you the clip here, and then you can figure out what is not correct with this. So there you go. That is one of the bullet curving clips from the show. Yeah, that one's definitely not how things work. Clearly in the show here, they are trying to show that if you spin your gun quick enough, as it shows here, you spin it fast enough, it's going to generate enough curves to go around a person's head. Yeah, that's not how physics works. And this all has to do with the fact that, okay, as you are turning the gun around and spinning your arm, yes, it has some angular velocity as it turns, but as soon as the bullet is fired, the only force acting upon that bullet is the ground, so really it just accelerates downwards. And you can make an argument that as the bullet spins, it curves, kind of like if you throw a baseball or a football and you spin it, you can get some curve going. But with a bullet, because bullets are designed to be pretty smooth, you're not going to generate much of a curve because they're traveling so fast. Maybe over a long distance, and if your bullet is not completely smooth so that it's got some grooves and ridges on it. But even then, as it spins around, because the bullet spins as it goes, it's designed so it travels in a straight path, not to curve like that. And if you have grooves on it, that's just going to throw off a normal bullet as it flies around. So this one, yeah, definitely not true. You try it. It's take a ball, spin your arms and throw it. It's going to travel in a straight line. It's not going to curve like that. So that is this one debunked.